All right, we are going to look at a new type of function today. So we've been focusing on linear functions for a while. We know that linear functions have slope-intercept form of y equals mx plus b, where the slope is right beside x and the y-intercept is constant. So that's our slope. That's our y-intercept. Okay, but I'm going to introduce you guys to a new type of function today, and it's called an exponential function, okay? An exponential function is going to have, it's going to look like this below, so y equals a times b to the x, okay? And we'll get more into that in a second. I want to show you a table of each. So we know that linear functions have a constant pattern, so they are adding or subtracting the same amount every single time. So for this one, our y's are decreasing by 8. Okay, so this is a subtracting pattern. We subtract the same amount every single time. Whereas an exponential function is going to be when we're multiplying or dividing every time. So it has a multiplying or dividing pattern. So in this table, we're multiplying by 2 every time. Okay, so if you look at the graphs below, it kind of makes sense. If we're adding or subtracting, it's going to have a constant, it's going to have a line, okay? So we're going to make a line. And it's going to increase or decrease much slower than if we're multiplying or dividing. So the graph on the right, this graph over here, kind of makes like a J pattern. You can kind of see a J because it's increasing very quickly. It can also decrease very quickly. Because multiplying and dividing allows us to do that. So if you were looking at a word problem like this, so a linear would sound something like the one on the left. John currently has $45 in his wallet. He spends $2 each day. So remember that each day is important for our slope, and then we're changing by the same amount each time. We add $2 we're subtracting $2 every single day. Okay. Versus on the right, it says each year Gertrude counts her tulips in her garden. Over the past few years, she's noticed a definite pattern in the number of tulips. Triples each year. So triples means we're going to multiply by 3. So if we started with 1 tulip, the next year we'd have 3. The next year we'd have 9. The next year 27, and so on. And that would increase very quickly. So look for that difference in your functions. The next part of this, we're going to compare some functions. So given f of x and g of x, which is linear? So we should be able to look at this and say, okay, I know that f of x is in y equals mx plus b. I see that 6 is my slope and 32 is my y-intercept. So I know that that is a linear function. Okay, g of x has an exponent, okay, and it's got a times b to the x, just like we learned a second ago was our exponential form. So g of x is going to be our exponential function. Our y-intercept of f of x, that one should be pretty easy for you guys by now. That's our constant term. It doesn't have an x beside it. It's going to be 32, okay. I'm going to hold off on this question, and we're going to look at the table, and then we'll come back to that. So we want to know the y-intercept of g of x. So if I'm using this table down here, so I kind of filled in our equation. So if I wanted to find x of 0, okay, we're just going to plug in 0 wherever we see an x. So for f of x, f of 0, I'm going to plug in, it's going to be 6 times 0 plus 32. Well, 6 times 0 is 0, plus 32 is 32, okay? And notice that matches up with our y-intercept, okay, because it's happening where x is 0, and our y-intercepts occur where x is 0. So if I want to find my y-intercept for g of x, I'm still looking for where x is 0. So if I plug in 0 for my exponent here, because that's where our x is located in an exponential function, we're going to have, remember, exponents come first in order of operations. So we have parentheses, but there's nothing to do in those parentheses, so we'll move right on to exponents. So 2 to the 0th power anything to the 0 power is 1, so 2 to the 0 is 1, times 5 is 5, okay? So our y-intercept for our exponential is going to be 5 because it happens where x equals 0. And if you notice, that number is in our equation. So that front number, that a term, is our y-intercept. Okay. We'll just keep on going here. So if I wanted to plug in f of 1, I would do 6 times 1 plus 32. 6 times 1 is 6, plus 32 is 38. Okay, and I know that my slope is 6, so I'm essentially just adding 6 every single time. So if I do 38 plus 6, I get 44. I'm going to add 6 again, and I'm going to get 50. Then we'll have 56 and 62. All right, for g of x, if I want to find g of 1, I'm going to just plug it in for x. So 5 times 2 to the first power. So 2 to the first power is 2, times 5 is 10. Okay, g of 2, we're going to do the same thing, plug it in. So 2 squared is 4, times 5 is 20. G of 3, we'll plug that in. So 2 to the third power, that's like 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. So 8 times 5 is 40. And if you notice here, our pattern is multiplying by 2, so we're doubling every single time. So if I double 40, I'm going to get 80. And if I double 80, I'm going to get 160. Okay. Notice this, okay. We are doubling our number. We're multiplying by 2 every time, okay. And there's a 2 in our function, okay. So that number inside of parentheses is going to give us information about our growth or decay rate. So rate of growth or decay. So how much are we growing or decreasing by each time? Okay, the last part of this one says, what is the smallest positive integer for x such that g of x first exceeds f of x? So exceeds means greater than, so it goes beyond or above. So if I compare my y values, so when x is 0, f of x is 32, and g of x is 5. So f of x is still bigger. Let's look at 3. So when x is 3, f of x is 50, g of x is 40. It's still bigger. But when we get to 4, things change. So f of x is 56, but g of x is 80. 80 is larger than 56. So the smallest positive integer for x such that g of x exceeds f of x is 4. So because at 4, g of x is bigger than f of x. All right, last part, let's look at some scenarios and see if we can figure out if they're linear or exponential. So the first one says a library has 8,000 books and is adding 500 more each year. So notice this says adding. So we're adding a constant amount each year. Linear functions are the ones with adding and subtracting patterns. So that's going to be a linear function. The next one says a gym's customers pay $50 for membership plus $3 each time they use the gym. So they're paying the same amount each time. We're increasing by the same amount each time. We're adding $3. So 50 would be our y-intercept, 3 would be our slope. That's also a linear function. A bank account starts with $10. Every month the amount of money in the account is tripled. First of all, I wish my money in my account was tripled every month. That'd be awesome. But notice that tripled means times 3. We multiply by 3. So if we are multiplying or dividing, that's our pattern. That's an exponential function. At the carnival, or at the start of a carnival, you have 50 ride tickets. Each time you ride, you must pay 6 tickets. So notice we're decreasing by 6 every time. We're subtracting 6. That's a subtracting pattern. And if we're adding or subtracting, that's linear. Last one, there are 20,000 owls in the wild. Every decade, the number of owls is halved. So halved means that we are going to divide by 2. Anytime you have a multiplying or dividing pattern, it is exponential.